So this is possibly the Earth's magnetic field. That's possibly orbital velocity, although it looks slow, right? Yeah. Is current really going to be flowing in this wire?
No.
When would it be flowing?
If it was a real line.
The instant it starts to move, there's no charge either way, right? It's a neutrally charged wire. So the instant we start to move that way, then the charge will just redistribute itself, right? And so as it starts to move, it's got the current will flow. So current only flows when it's accelerating, which is sort of an interesting thing, right? At a constant velocity, if it's been at that velocity long enough, it's at a steady state. The current has already been redistributed. The instant it stops moving, the charge goes back because like charges repel, right? That distribution is only there because of the magnetic field exerting a force on it. Yeah. Yeah, you got it. Yeah. What if this is your brain? Does your brain conduct electricity?
Yeah.
Yes, it is an electrical device. Okay, we know this. We know that.
Have it at school?
What?
So we're not allowed to have it at
No.
school?
Yeah, no. Right? Okay, so this is an interesting thing. The interesting thing, and then there's big nerve bundles, especially like the optic nerve. If you work in very strong magnetic fields and you move your brain through those fields, that is, you're trying to walk from one side of the room to the other in these fields, you're actually making charge move around on your nerves, right? And your brain tries to make sense of this. And so people that work in these strong magnetic fields will sometimes see things like little flickers and flashes and stuff in their vision that aren't really there, because they're inducing currents in their nerves. I don't think there's any long-term harmful effect. I just wouldn't choose to work at a place like that. Charles confirms this. He worked at a and I'm not saying that explains how Charles is, although I think it does explain some of the Charlesness. I'm kidding, Charles. Okay, the wire has a potential of 0.215 volts. The right end is the positive side. So what is the magnetic field? Which direction is it? Holy sig figs, Batman. We have 3 sig figs, apparently. I get like 0.05 Teslas. That's right. And yes, you're right about the direction though. Yeah. Now we have 3 sig figs, so give me 3 sig figs. 502, 501. Oh, Teslas. Yeah, I got that. And then, yeah, you got it right. Yeah. Yeah, which way? Yep. Yep. Yeah, give me 3 sig figs though. That's right. That's 1. That's 2 sig figs. Give me 3. That's 1 sig fig. What? That's only 1 sig fig. Give me 3.
Actually, that's 2.
That's right. No, it's not. Leading zeros never count. Yeah, and then the last digit's a 1, but yeah, the last digit would be a 1. So now which way, right? It's like there you go. Yeah. Down. No, the direction is not down.
No.
Nope, not up. That's right, yeah. Okay, so now let's all do the Tai Chi here, right? Okay, the velocity is down, index finger's down, okay? And now the force has to be to the right side. Okay, so put your thumb to the right. Which way is your flip them off finger pointing? It's into the page, isn't it? Yeah, this guy's... Okay. You did both? Good for you. May always make an even number of mistakes.
I was thinking vertically down.
Yeah. I knew you were, but I was not going to accept that. All right.
And now my
Video of the Meissner effect. Magnet approaching eddy currents. Yeah, this is a cool thing, right? So this brings us to some very cool things that we can talk about here. Okay. So you put the caps on your pens. I don't have any more whiteboards. But if you imagine that this stool is a magnet, a giant magnet, okay, and it really helps. Can you guys that are borrowing pens every time, can you go be responsible and go purchase a pen?
Oh, I have a pen. I just forgot about it.
Buy
Okay.
one, you losers.
This thing is a magnet, and I don't know if you can tell, but let's pretend this is a magnet, and it really helps to draw an N on something, right? So if you see stools with N's drawn on them, they're magnets, you know? Now, if I take this magnet and I make it approach the board, this board, by the way, is a piece of iron. It's actually a piece of sheet metal that has an enamel paint baked onto it. I know this because magnets stick to this whiteboard, okay? And if I approach this board, boom, like that with that magnet, does it want that magnet approaching? Yeah. No, it's never been here. We don't like that. We can't accept any change of any form, right? Okay, and so how do you oppose a North Pole magnet approaching the board? You present it with a North Pole magnet, and now the question is, where's the wire? Well, the whole board is a wire, isn't it? Okay, and so what happens is you get these little mini vortices of charge all sort of going anti-clockwise. We know which direction they go, but they go in, I don't know, I think this is something that people get advanced degrees in, is what eddy current damping does. In fact, there's a guy named Stephen Gaskill who did his research project on eddy current damping, which we're talking about, right? And so it's a complex thing. But just suffice it to say that there are little bitty eddy currents here, okay? And they're all going anti-clockwise, you know? There they are, right? And they all oppose the motion of this stool toward the board. There they are, okay? In fact, the board is actually going to heat up. If you could look at it thermally, and if that were a powerful enough magnet and I made it approach quickly enough, all of those little currents would die down, their energy would turn in, and this would heat up the whiteboard. Isn't that interesting? In fact, they make devices that sit there, just enormous electromagnets that just sit there and change the flux back and forth really fast, right? That induce eddy currents in the metal that heat it up so hot that the metal melts and then they fuse together. It's called welding, inductive welding. They have inductive welders. You can stick two pieces of metal in between the poles of this magnet where the flux is changing really fast. It induces a current so high that the metal heats up white hot, melts together. They make these things. They're called inductive welders. Isn't that cool? So with electricity, you can arc weld, right? Spot weld is where you just have two electrodes that go together and the current just flows through there and it melts it, right? And then inductive welders that don't even have to touch the metal, right? They just get close to it and induce a current, a little spot, right, where it focuses that vortex of magnetic field, right? Heats up white hot, the metal fuses together and it's welded. Yeah. Of inductive welding. I've got a YouTube video of the Meissner effect, which is really very cool. I don't know. I'm not going to search around for a video right now for whatever. Okay. So this is a cool thing, right? And I've got all sorts of examples of this. Obviously, the eddy current stuff is going to resist. It's going to slow. It's a dissipative thing, right? It takes energy away from stuff. So as I push that stool toward, or that magnet toward the whiteboard, I feel this resistive force. I mean, not really, because it's not really a magnet, right? So this is the demonstration that I purchased from the scientific catalog, and it's not really very good, but I'll show it to you because it's kind of cool, right? This is a tube of glass. This is a tube of aluminium, okay? And to show you that it's aluminium, I'll just put this thing here. This sticks to, this sticks to this base,